Okay, so I think we're good to start. So yeah, why don't we get started? So hello, I'm Michael Van Pan. I'm a professor in computer science at UBC and deputy director of CAIDA. Yeah, so today we're absolutely delighted to have Dr. Philippe Pasquier present, and so he is an associate professor at Simon Fraser University at the School of Interactive Arts and Technology. So there he directs the meta creation lab for creative AI. And so it really works completely at the intersection of art, science, and technology. And so that's a topic near and dear to my heart because in my own work in the computer graphics community, we also aim to work at that nexus. He's aside from publishing in many scientific venues, I also uh, exhibited his own artistic work in many prominent venues, including Ars Electronica in Austria, which many of you may have heard of. Also at the Centre Pompidou in France, and Musée d'Art Contemporain de Montréal, and the Sydney Biennale in Australia, and more. Um, so if I really wish that all of us were such polyglots that we could manage to do those things and make contributions to science at the same time. Fantastic. Um, yes. So today he'll be presenting on creative AI. So on the partial or complete automation of creative tasks. And so welcome, Philippe, and I very much look forward to the talk.
Thank you, Michael, and thank you for the invitation to CAIDA. I'm really happy to be here with you today. I'm going to share my screen to get things started, and I'm going to start my little timer here.
Looks good. We can see the screen. We can hear you well.
Yeah. Perfect. Yes, so I'll try to do a sort of a broad introduction to creative AI, at least to creative AI, the way we conceptualize it and the way we practice it at the Meta Creation lab today. From the industrial revolution to the digital one, which is very much ongoing right now, the idea of inventing and using machines to partially or completely automate tasks is really something that is fundamental, a fundamental feature of humans and humanity. And in recent years, of course, people at CAIDA and this audience would know and have witnessed the rise of AI as we, with the computerization of society, we are increasingly automating tasks, and AI systems have been really successful at automating a growing number of complex tasks in which they routinely outperform humans. And here and throughout this talk, I'll be talking only about weak AI and this idea of automating specific task as opposed to what's sometimes referred to as strong AI, this idea of ongoing machine with sentient intelligence, which I think is an interesting research project, but which we're very, very far from getting anywhere close to. But when it comes to weak AI, a lot of tasks have been automating. Often these correspond to rational problem solving, tasks for which there is an optimal solution, tasks for which there is an objective function, a set of well-defined goals. Sometimes it's a Pareto dominant front. Sometimes it's all sorts of measures of optimality that help us in the search for solution and in the automation of those tasks. At the Meta Creation Lab and in creative AI, as a subfield of AI, we are instead focusing on creative tasks, which we define, in fact, as being specifically those for which there's no clear best outcome. There's no such thing as the best graphic design a priori, best music composition, or an optimal drawing, a Pareto dominant painting, etc., etc. Yet, one of the main, if not the main use of computers nowadays is not rational problem solving, although it is still very, very important indeed, but it's entertainment and creative computing, and a lot of creation of artistic and creative and design assets through computers. And creative workers in that domain are left alone clicking on buttons in software, and there's very little AI, very little machine learning in those areas. So that's really what we try to do at the Meta Creation Lab, is to look at the partial or complete automation of creative tasks. Typically, that means we're going to use generative systems often, but not always, using machine learning. recently increasingly deep learning. The type of formal problem that we address are things such as style imitation, the idea that if you have a corpus representing a certain style, then you want your system to generate new instances that an unbiased observer, that is you or I, would classify as belonging to that particular style. And once you have algorithm to do style imitation, then you can play around and do style interpolation, style combination, maybe style transformation, style extrapolation, style transfer. And you've heard for most of you those terms before because they became popular in the last few years. So today I'm going to focus on two broad families of applications of those creative AI algorithms. The first family will be computer-assisted creativity. This idea of embedding creative AI algorithm into existing creative software so that the user can interact with the system and get to create faster, better, or to create differently. The second family of approaches I'm going to cover today are embedded generative system, when we want the creative AI algorithm to actually generate new content on the fly online. And that will be critical for applications such as games, for interactive systems, interactive installations, and interactive artworks. So let's start with this first family, computer-assisted creativity, sometimes referred to as co-creativity. And by the way, creative AI is also sometimes referred to as computational creativity. If you talk to artists, they will talk more likely about AI art or generative art. So depending on what community you're talking to, you'll have different appellations for these emerging fields and ideas. So first family of applications, computer-assisted creativity. And let's start with something we've been working on for over a decade now, computer-assisted composition. About a decade ago, with my colleague, composer Arne Engelfield, we were working on style imitation, as I just defined it, for harmonic progression. And we were using at the time Markov chains and design systems such as the one you see here, where you load a particular corpus, maybe some music from Chopin, and then you decide on a request, a tension curve, and some parameters that are user-defined, and you would generate chord progressions. If you don't like it, then you generate another one, you make another request, and you generate another one that way. And that's a thread throughout the creative AI work that we do. That way you don't have to make content, you just get to select content. You're not really the creator, you're more of a curator, and you interact with the system at that other level. This is a type of output of that system that generate only sequences of chords. And here is another example from the same corpus. And then I'll do a little discrimination test for you, a mini Turing test for music. All right, so these are two examples. In fact, only one of them has been generated by the system based on a corpus from Chopin, and the other one is an example from the corpus. Can you tell them apart? Well, it turned out we did experiments, empirical experiments, and people can't tell them apart above chance. And even musicians, well-trained musicians can't, although musicians would find a lot more arguments and reason for their choice, but they would still be not better than chance actually determining. So we have, for a long time now, for over a decade, human competitive systems for some musical tasks. So after harmonic generation, we did melody generation, rhythm generation, all sorts of subtasks of music composition in the symbolic domain, to converge recently to this much more flexible and powerful model using a transformer called the multi-track music machine. And I'll play a little video exemplifying this. All right, so that is the latest in computer-assisted composition type of model that we have. So I'll go in a little bit of detail of this one, and then after that, I'll ramp up to some other example and the second family of approach. So computer-assisted creativity. Here we have a model that is trained on a big data set of composition. It's symbolic, so it never heard audio. It doesn't generate audio either, just symbolic scores, reading and generating scores. And so it's based on a data set that is yet to be released, the largest MIDI score, if you wish, data set that comes with a lot of metadata called MetaMIDI. And then we trained simply a transformer with 6 layers and a model for 4 bars and 8 bars, and then the sliding windows that allow us to generate longer parts. So with this type of model we use, and that's really the only innovation here, is a new tokenized representation for music that capture quite well the fact that bars are made of sequence of notes, and that tracks are made of sequence of bars, and that those tracks are stacked on each other to correspond to different instruments. And with this model, as you saw in this little video, you can load existing MIDI files, or you can generate from scratch. You choose an instrument, maybe you load some Chopin or some Beatles, and you decide to add some violins or add a bass, whatever the case is, and the system is going to generate those new tracks conditioned on the existing one to make sure that it makes musical sense. You can regenerate tracks as long as you want, and that's really what's new with those systems is all of a sudden you get to generate and make requests to the system, and if you don't like it, you generate again. And then you can selectively regenerate part of the composition. Oh, I really like this bass line, but not the beginning or not the end. And then you select what you want to regenerate and you get new option there. And you can do that on longer composition as well. You have also a number of controls that I'm going to talk about in a second. So this model, when it comes to multi-track, is really state of the art and goes a little further than all the other models out there. And in the current version that we're developing with industrial partners, we're working on controlling also the note density, note duration, time signature, which is important for composers, and all sorts of other details that are really important for composers to make the system and the model usable. Importantly, we're also interested in affective computing and in controlling how the music generated will be perceived. What will be the tension, the arousal, the valence? Is it going to be happy or sad music? Is it going to be calm or energetic? Being able to control that and eventually control it in real time will become important when we generate things online, for example, for video games. So once we have a model that works, and this model is a way better composer than me, and possibly the best composer I know, actually, and it works really fast. And so then the problem is not so much the model anymore, it's more the interface. And how do you get to use this model and what for? And so we start working on human-computer interaction for AI, which I believe is going to be strategic for the next 10 years of human-computer interaction research. How do we embed AI into all sorts of working process, but in our case, in creative process of creative workers? So we've been working on a number of interfaces. Our own interface is called Apollo. It's a web interface. It's still a little bit in development. There's been publications about it, but it's not quite ready. And we're really interested in this idea of having a corpus manager, managing different corpora, being able to do style interpolation, and being able to do batch generation. That is not only to ask, oh, give me a violin for this composition, but more give me a Tazen variation on this composition, and then rank them according to this other composition. So working with quantities of data and music that you couldn't work with other approaches. And then you can stream the MIDI to your favorite digital audio workstation to get it to sound good. So we're working right now with the industry on deploying these type of approaches in existing digital audio workstations, as well as in some hardware. We have collaboration with synthesizers makers as well, which are interested. Because often in music, a lot of the users never finish a song because they don't really have all the compositional chops that it would take to do so. And it takes really a lot of time to enter everything by hand. How many times are you going to start from scratch again, undo all you did and start clicking on buttons one by one forever? Well, the answer is like not many times. And so this type of computer-assisted creativity system really have a potential there. We've done that in the past with previous models, but we're working now with this new MMM model. I'll be dismissed not to play some of the examples of music created with the model. So that's an example of breakbeat music. Here is an example of actually my own music, an album that's going to be released in a few weeks. So we are ourselves using our systems, and in the next steps, we're really interested in getting a lot of empirical research done with existing musicians and composers, and try to evaluate really the quality of the system generation, of course, but also how much control the user feels, how much expressivity does the composer feel there is, authorship. Does the composer still feel that it is or her own music at the end of the process? Does the composer trust the system and can anticipate and understand the system enough to control it properly? All those questions are going to be crucial for the acceptation of those systems in real-world applications. And then finally, on the MMM, we also had a fantastic student, Kel Plutt, who is also a composer, leading our team into entering the 2021 AI Song Contest. And that's an example of a completely different style of music generated by and using MMM. It's more Californian rock in this case. I'll play an excerpt. All right. So for the sake of time, I'll move on. So that was computer-assisted composition, co-creativity, embedding creative AI system into composition tools. We also did that with sound design. And sound design is a bit more complicated because it deals directly with audio in, audio out. You have to put together on a timeline a variety of sounds. So we have this system called Audio Metaphor, in which instead of searching your hard drive and in your data bank of 1 million sounds, which one you want to use, you type a request to the system. Kids are playing in the park on a windy afternoon. How long you want the soundtrack to be? What is the perceived emotion of that soundtrack? Does it start sad and finish happy? Is it calm or is it energetic? And the system will retrieve sounds, will segment them into background and foreground sounds, will classify their valence and arousal, will mix them together so as to generate both a mix that you can download in your digital audio workstation and work on, and or render it directly if you are to use it directly. If you show that to a sound designer who is using Pro Tools or equivalent tools all day long, they will want to use it, because just searching, retrieving the sounds on the hard drive and cutting them is hours and hours and hours of work. And the system will do it. And if you don't like what it did, it will do it again for you the second after. So here are example of output of the system with a request such as a waterfall in Thailand might sound like this. A city in the bush might sound like this. And of course, for this system, there's always a way to abuse them. Artists love to detone or to use tools the way they're not intended to be used. And for example, you can have more abstract requests like that. In fact, this system is also used to make interactive artworks. And there's a piece opening in Montreal next week at an art center called Eastern Bloc using this system. So that's an example of maybe more evocative, more abstract sound design using the system and pushing it. So that was computer-assisted sound design, and to finish on sound and music, and we also looked at computer-assisted sound synthesis. Sound synthesizers are amazing machines, and they're very, nowadays, very versatile, to the point that the designers of a given sound synthesizer typically do not know what sound the synthesizer can or cannot do. In fact, this little synthesizer here, the OP1 by a Swedish company, Teenage Engineering, can do 10 to the power 80 different sounds or sound presets. And there's, that's very close to like a couple of order magnitude less than the number of atoms in the universe. And so if you start searching manually for a sound, it might take you a while. So we developed machine learning so that you give me a wave sound, and I give you the preset for that synthesizer that does the sound the closest. And it turns out they didn't know this synthesizer can imitate a grand piano pretty well, but it does, etc., etc. And so here we again have a tool that really goes straight to what is the roadblock for composers, be they novice or professional. We also started looking at deep neural network for sound synthesis. And here I'll be very short because, to be very truthful and honest, right now, the audio quality of neural networks when it comes to audio synthesis, if it's not for voice, is not good enough to be used by musicians or professionally in any sort of way. So we are holding out a little bit here and doing the research to try to improve a little bit reconstruction quality and the type of pipeline that I use right now that are not satisfying. But we've been looking into it. And then, of course, we didn't stop necessarily at just music and sound, although it's our specialty. 10 years ago, we were already doing style imitation and style transformation without neural networks for visuals. And I want to mention here the work of my colleague Steve Di Paola at CIAT. If anyone is interested in visual generation, this is technically quite better than what neural networks will give you nowadays. And even though we all switched now to neural networks, so as style transfer back in the days, we obviously switched to neural network as well. And I've been collaborating with a local company, Vancouver, that just relocated to Toronto called Generate. And I recommend checking their app here, in which they allow the user to train their own filters, which is interesting. So those are all examples of computer-assisted creativity, where we add creative AI algorithm within a tool that a user, being a beginner or a professional, will interact with that tool and generate content through this interactive back and forth with the system. The second family of systems I wanted to cover today and talk about today, as mentioned at the onset of this talk, are real-time embedded generative systems. More complicated because then they need to be online. So why would you do that? Well, the truth of the matter is the whole motivation for generative AI in general is the explosion of the number of assets needed when going interactive. And what I mean by that is we are moving from a world where we were inundated and still are with linear media. You look at a picture, you read a book, you listen to an album. If it takes 200 people to make a Pixar movie, every second can be looked at, it's fine to do everything manually. If you develop an interactive experience, let's say World of Warcraft, and you have 20 million players per week that play on average 15 hours each, how many characters do you need? How many animations do you need? How many hours of music do you need? How many scenarios do you need? Et cetera, et cetera. And all of a sudden, it becomes, for the industry right now, a real bottleneck. And that's why AAA AI games, for example, are now the most expensive software that we have, being more expensive than film productions in a lot of cases. That's the main reason. Explosion of the number of assets needed. We need to go generative somewhat. And then why do we need it online? Well, because we want eventually to have adaptive experience and generate the right content for the right user at the right moment. I'll take the example of games, but it works for education or any other interactive experience you can think of. We need to stick to the flow. This notion of flow, imported from psychology, is a simple idea that if the experience is too easy, not changing enough, not corresponding to the level of the user, then it's going to be disengaging. If it's too hard, too challenging, then it's going to be off-putting and disengaging as well. So you have to keep the user in this notion of flow. And it turns out that every user is different. Some user will stagnate for a while and then all of a sudden progress really quickly. Some user will get very advanced very quickly and then plateaued. Your system won't know that unless it monitors this particular user and generate the right content for the right user at the right time. So here is the motivation for the second family of systems, which are embedded systems. So we started, again, exactly a year ago, getting some award-winning game level generation systems that are really using this exact idea and managing the tension curve of the game, tension rising when more and more complex jumps and operations are needed from the player, and tension being released when things are becoming simpler for the player. Once you have a tension curve for your game, then of course it is tempting to use it to also have the music adapting to that tension curve. And you certainly don't want to play super happy music if a player has been playing for a number of hours a given character and is about to die. And so we want to track what's happening in the game and generate accordingly. We did empirical studies, by the way, to show that this matters and that it changed the experience of the player. We knew that for film, because when you're crying in a movie, it's because of the music, and it's been really well studied. We didn't know if it was the case for interactive experience, because your body, your mind is busy. It turns out it does make a difference. There's a paper there called Music Matters at the IEEE conference. So those are examples of real-time online embedded systems. The main type of system we worked on there is for music generation. We've been working on musical agents with an architecture called Masom, which is an agent that is being trained by simply listening to music, like a lot of amateur musicians are. But he can listen to more music than a human can. And then he's gonna find and memorize all the sounds that he's been listening to, isolating them, classifying them in a self-organized map, a big sonic texture memory, if you wish, and then learn temporal models of, if I was Chopin, after this sound and this sound and this sounds, what is the sound that I would put next? And those temporal models in a way capture the style of various composers or various music, and then we can recall those models for the agents to generate. So here's an example of the agents generating music in real time, live on stage at Ars Electronica, and talking to a system developed by a collective in Istanbul called Uç, and the system, their system generates the visuals as well. All right, so that's an example of the system generating content, and that allows for an experience and a tightness between the visuals and the sound that you wouldn't get if you would do that manually in real time. Of course, what's interesting with musical agents is really to interact with them and not letting them on stage alone like that, interacting with other systems. And that's really the idea of a musical agent, is it will listen to music, there will be a machine listening module, and then eventually the agents knows what you've been doing before and what the other players have been doing before, knows what it's been doing before, and eventually if there's a score, know what's coming up in terms of harmonic and progression, and generate its own part in real time as we move along. And that's exactly what we did with Masom, and we had the chance with now Dr. Kiven Tatar and myself to play on stage numerous occasions, a show called Revive, where we somewhat provocatingly as the model to play in the style of famous dead composers. And the piece is called Revive because we get the chance to improvise on stage with these agents imitating those composers or trying to revive those composers in a way. So we've been going live with that. And then recently, because we were interested in that agent, a collaboration with PhD students at the Norway Academic of Music, I believe, Noto Thiel, just got 3 days ago the Best Paper Award at the New Interface and Musical Expression conference. We've been building on top of this idea of agents to see if we can, as a creative partner, have different types of behavior of the agents and be able to control the behavior of the agents, asking, hey, I want to train myself doing solo. So you're going to do accompaniment now, or you're going to shadow me, or you're going to mirror me, or you're going to complement me, and how to eventually give feedback to this agent so that it progressively learns a little bit what you like and what you expect as a co-band member, if you wish. So we're working on this notion of musical agents continuously, and it is not easy, but we're making great progress. Of course, the MMM model is going to be instrumental to help us go further in the near future. Alumni from the lab have also done online generation, and there's an app right now called the Allo app, which is interesting because it's goal-oriented. You tell the app what mood you're in and what your goal is. Maybe you want to go to bed, maybe you want to focus and work, and it's going to start generating music, and you have a bunch of interactive control, and you can eventually drive the AI to generate the type of music you like and that works for you or seem to work for you, save this, and then go back to it later if and as needed. So again, whether it's for professional use or for every user, these are embedded generative systems that generate content in real time so as to generate the right content for the right moment and the right experience. We've been also dabbling into movement generation, which I know, and I'm a big fan of Michael's work in that area. We were interested in generating movement and being able to control the effect of what's being generated. So we did motion capture of a number of actors and characters using asking them to express a variety of emotion. And we made experiment to see, can people recognize my emotion just by looking at my skeleton moving? No facial emotion recognition here. It turns out people can, and the inter-rater agreement is fairly high. Therefore, we can train a machine to recognize emotion based on your skeleton's movement. And we can ask that machine to then generate movement based on what it's been learning. And what's interesting is it's online, it's controllable in real time, like a movement controller would be in a video game. And very importantly, it allows to move from one movement signature, mine, for example, to the movement signature of any other performer. And in fact, it's sort of going to control, it's going to build a manifold, a latent space that you can navigate that will allow eventually to solve that problem I was mentioning earlier, which is if you need 1,000 characters, you probably don't want to mock up 1,000 actors. What you want is to mock up very different movement styles and then move in that latent space to generate a variety of movement styles within that manifold that you've been defining. We can also control here the valence and arousal. This is restricted constraint, but these Boltzmann machines that are being used in the background there. So that's WalkNet. And then because we do so much music generation, we're also interested in looking at whether we can have multimodal networks where you generate movement based on the music or you generate music information based on the movement. And here is an example of this network called GrooveNet. So yeah, so this is generative dance on generative music. Interestingly, as you see, there's a human way of moving. So some of the human dynamic is being captured, but there's also like elbow and hand movements and super rapid arm movements that are sort of not very realistic looking, which for creative application is not a problem, but eventually those models will need quite a bit more work. And as per usual, quite a bit more data, which is the one thing we seem to miss in the context of movement generation at this stage. Then we worked on generative music video as well. We're interested in doing automatic vidging. We have an exhibition right now in Istanbul at Akbank in Turkey, which is a great gallery there, showing some generative video, but I will skip that for the sake of time. Oh, I'll play a little excerpt actually. So this is more abstract visuals in a contemporary art. contemporary art gallery and contemporary art style, we are working on, the video generation condition on sound in real time, because we would love to have better visuals for our own performances and also for other artists we're working with. But video generation is a bit complicated and challenging still. We're working on it. So all those systems to be adopted by the industry, we need to, and as computer scientists, as scientists ourselves, we need to ask ourselves the evaluation problem. How good are those systems? How are they perceived and all that? So I won't get into that because this is more technical and a bit dry eventually, but suffice to know that we've been developing, I think, about 8 to 10 different research instruments for formal evaluation of creative AI systems, and it is challenging. And what's interesting as well to note is there's not only the scientific evaluation of the quality of the system, the convergence of your algorithms, those type of things. In reality, the evaluation in co-creativity, as for online generation, would be the author, artists, designers, computer scientists. They'll be deciding, oh, the system is good enough, let's chip it that way, or let's make an album with it, or let's make an experience with it, an interactive experience. And then the users, peers, experts will get to decide, eventually the audience, the media, because in the art world, you might not have a lot of proof or empirical experiment, but if you sell a lot of albums, you'll still be considered successful. So those are informal, real-world evaluation methods, if you wish. Some methods are a little bit more formal, even in the real world, with media, critics, and journalists, professional of this informal type of evaluation, but also peer reviewers, curators, and jury. You want to get funding as an artist, you want to get invited to festivals, you want to get grants as a researcher. Those are all semi-formal evaluation system. And eventually, of course, as scientists, we're interested in empirical evaluation, be they as well as formal analytical evaluation. And so we've been doing quite a bit of that. It is really challenging. And then I'm going to loop back here to the very beginning of the presentation. The main reason why it's challenging is because creative tasks are those for which there's no notion of optimality. And so all of a sudden it's going to be complicated. There's going to be a subjective cultural dimension involved in whatever judgment as for the quality of the generation, and the framing does play quite a bit of a role into whether this is acceptable or not. And the discourse around a particular artifact is really of importance when it comes to creative tasks. And then there's practical reason. You have to choose a corpus. Different corpus will give you completely different outputs, the parameters. In fact, you have to choose a sample output. So the generative system can create ad infinitum. Some of it will be great, maybe. Some of it will be of bad quality, possibly. And then the creative process. How, where do you integrate this algorithm into the workflow? And then eventually the choice of interface. And so the user experience and the usability of the system as a whole for people. So there's very many dimensions to the problem of evaluation when it comes to creative AI systems. And I'll keep it at that. And the second dimension of evaluation is whether those systems will be accepted as such independently of their performance. And we did quite a bit of work, 2 studies already regarding the bias for or against computational creativity. Is it the case that if you reveal that a particular artifact has been computer generated, is it judged to be less interesting, less valuable, or less creative than a human generated one? There was, and there's been anecdotal evidence of that in the past. Famous music generation researcher David Copes did have issues in the 80s finding an orchestra that would agree to play his computer-generated scores. Literally, no one would want to play those scores, even though they are actually of very, very good quality and high standard, and now there's no problem with them anymore. But at the time, it was a little bit too subversive to be acceptable by the music and the musicians themselves. So there's so far been 5 studies regarding this bias for against computational creativity. And to be very frank and synthesize it for you, nothing conclusive really came out of it. And it seems that this bias doesn't really exist anymore, especially if you correlate things with computational literacy. That is, people who actually know how a computer works, which is increasingly the case, do understand that behind those systems, there's programmers and there's people using those systems, and it's usually years and years of work. And so it's not just the computer coming up with new music out of nowhere. All right, so I'm reaching almost the end here. So why does it matter to do this creative AI? Well, it is scientific research, trying to understand, formalize creative processes. It is also, I hope I demonstrated today, applied research, which has very many applications in computer-assisted creativity, enhancing the creative workflow, making creation more accessible for those who would not be able to generate those artifacts, controlling expressivity, flexibility, authorship. There's a lot of work remaining in the domain of co-creativity or computer-assisted creativity. And then the second family I presented today, which is also very applied, is embedded generative systems to enhance interactive experience, be it in gaming, in health, in well-being, in education. And then finally, it is in itself a major development in art and in culture, at least in the Western world, which is influencing right now every field. You will find in every artistic field you can think of an AI-related development. And it's also creating new fields and new type of practices that just didn't exist before, like AI art and things such as live coding, the idea that people start playing code as opposed to playing the guitar. And of course, if the computer is the medium of the time, then it makes complete sense that artists will appropriate it, and then new practices will be born out of it. Okay, so there's a whole ecosystem around creative AI, ranging from scientific research to artistic practice to the industry. Lots of companies. There's just a small fraction. I didn't have that much patience to gather all the logos out there, but there are literally hundreds of startups right now working on creative AI applications. So of course, it raises as well a little bit of a pushback. And as long as there's been technology and great advances in the co-evolution of humankind and the tools that they develop, there's also been pushbacks and fears. Here you got this illustration of what was happening when the Luddites in England were rebelling against the machinery that were invented for sewing and making things. But in artistic domain, it's been the same. In the early 20th century, when musicians were replaced by music players in cinema, there was quite a bit of pushback at the time. Here you got a robot grinding up musical instrument and those type of illustration. And it turns out, of course, that now nobody is really shocked or annoyed by the fact that we don't have live music in movie theater. So things are evolving, and the computerization of society has been real. It is real. It's not been democratically voted upon, but it turns out everyone is asked to use a computer about 8 hours a day, every day. To simplify, to caricature things a little bit. And a creative worker, this is a little bit the workstation and what it tends to look like more and more. And now we have this army of creators that are left clicking on buttons to try to get the computer to do what they have in mind. And it's usually much, much more painful than it should be. And so the idea with creative AI and embedding it into either directly the user experience or into the experience of the creative worker themselves is to eventually relieve a little bit those workers by allowing them to produce more efficiently, eventually create different things and be able to iterate more often on their creation so as to get better outcome. So in conclusion, technology has always shaped us. Personally, I'm rejecting the fears of AI taking over, especially because I don't believe in strong AI for a second, at least not at this stage. And I do believe strongly in the humanist tradition of anthropocentric instrumentalism. We do develop the tools we feel we need. And if we don't think we need them, then we should have a debate about it. And I think there's a lot of healthy debate happening around the applications of AI nowadays. And it is certainly true in the creative domains as well. But overall, the computerization of society has deep implication. And I believe that we can and possibly should harness the power of machines to expand and support our creativity. So I'll conclude by saying and reminding you all that this is obviously work that is done in collaboration, not only with my students, but also a lot of different colleagues across the world. Not all of them, I could squeeze the picture in there. If you're interested in knowing more, there is a MOOC class on this fantastic MOOC platform called Cadence that was started by CalArt a number of years ago, in which I teach computational creativity and creative AI. There's 2 different courses there that are free for the first one, and the second one you just have to email me and I'll get you in. And then in terms of announcements, the second joint conference on AI music creativity will happen in Grasse later on this summer for those who are interested in AI music. And then there's a special issue of the Journal for the Simulation of Musical Creativity that is out as well. I'll be giving music AI tutorial at ISHCAI, as I often do, for those who are interested in a more traditional AI conference, the International Joint Conference on AI. And then also, for those who are interested in movement generation, I also point at the MoCo community, the movement computing community, that has a focus on the perception, the generation, and the manipulation of movement information. So with that being said, I think I'm reaching my time. And so I want to thank everyone for your attention on this very sunny day here in Vancouver, and also thank the funding bodies here in Canada that make this work possible. Thank you.
Okay, great. Yeah, many thanks for really interesting talk. Fantastic. Yeah, so we have time for questions, and so I'm happy to keep track of chat, or let me just get started with one question. So can you comment a little bit on how much data you need for some of these methods to work, and I guess specifically for the let's see, the audio metaphor, was that trained on text captions of audio clips in order to be able to then invert that?
Yeah, no, very
great.
Yeah, very good question. I think I mentioned when I was talking about sound synthesis that deep learning is not good enough yet for generating audio at the quality we want. And so audio metaphor, surprisingly, is not a deep learning based systems, unlike MMM. And so it's actually using a database of sound that have been annotated, and we're using, there exists a number of such databases, but we use a free one called freesound.org. And that's, I think, the largest sound asset, free sound asset database in the world. I wouldn't know the exact size, but it's really, really, really big. So basically what the system does is that it really does a collage of existing sounds like a sound designer would do. It just does it automatically. And so this particular system is not deep learning based. And that's something that I like to remind everyone of is, deep learning is trendy now, but in a lot of domains, my favorite and arguably the best AI algorithm is, as for now, not a neural network.
Okay, fantastic. So I'm going to take, let's see, 2 questions on the chat, and then Jean-Pierre Briot. So from the chat, creativity, at least human creativity, is often driven by emotions. How can we move forward to create systems that take account of induced emotions?
That's a very good question. There's quite a bit of work left in affective computing to necessarily get there, but I tend to agree with the statement. Now we are, as I mentioned, really interested, and we made great progress when it comes to perceived emotion. And so I get my system to generate output, and I can control how you're going to perceive it. Now in emotions, it's complicated quickly because there's how I feel, what I express. So I might feel sad, but try to look happy because I'm an actor and I need to, or because I don't want to cry in front of you. Then you're going to perceive what I express or not. You might fail to perceive it. And then it's going to eventually induce an emotion in you, right? So there's all those dimensions, and we are really focusing on how you're going to perceive the stimuli. That's what we've been successful at doing. We can generate music and guarantee that on average, humans will find it, let's say, happy or sad, etc. Now, will that provoke that emotion in them? That's a completely different research story, and more something that I would leave to psychologists and people in cognitive science, because then there's a physiological dimension. There's all sorts of complexities that I personally don't want to deal with at this stage. But there is certainly a trend into that direction of using those AI systems for regulatory purposes. I was mentioning the Allo app, in which the goal is explicitly to help you focus, help you relax, help you sleep. In that case, it makes real sense to not just look at how the music and the stimuli being generated is perceived, but also to check what are the physiological implications and to see if it actually does work. And we're really interested in those type of regulatory applications, because for those adaptive systems that are online and that can eventually evolve with the user and deliver the right stimulus for the right person at the right time, there's a massive market there, as you can imagine. Starting with waiting rooms waiting rooms of hospitals and doctors where people are getting stressed for no reason. If we could just relax them, there'll be less misdiagnosis, and there would be all sorts of benefits, etc., etc. So this is definitely an interesting research area, but as I said, not one that we explicitly tackle now, although we have ongoing grant applications that are going in that direction.
Yeah, great. A question from Andy Worth. Let's see, Andy, would you like to ask your question, or I can ask it on your behalf? Up to you.
I can ask it, sure. So you mentioned that judging optimality for these kind of algorithms is difficult. So I'm just wondering, how do you do that? Is it based on specific artist desires, or is it just to make a general application that can implement whatever its user wants it to be? So how do you approach that task?
Yeah, so yeah, exactly. So there's several ways to approach it. Like sometimes you just reduce your problem into an actual rational problem solving. Like for example, the problem where we're searching for a preset that match a given sound. So that's like pure rational problem solving. You know, I have an optimality, I have a similarity function between what the synthesizer does and things. But for the more creative tasks like composition, generation of soundscape, all of that, it is left to the user to select and to curate. And it turns out that generation is quite easy and curation is a lot harder, right? So it's aesthetic judgment is something that there's a massive, I do make courses around that, but aesthetic judgment is hard to formalize. Even with machine learning, it's really hard to not fall into the average problem. And so it's down to aesthetic personality of the user typically, or you can give aesthetic personality to your system. And you can overtrain, and a lot of artists do. You can train the system so that it has a particular signature. You know, if I train my system on only Bob Marley, it's going to give me some Bob Marley, or some very, very hard to distinguish from Bob Marley sort of content, right? And so that's where the creative use really starts. And we capitalize on the fact that humans are really, really good at telling what they like, but it takes a lot more time to generate it or to write it down manually yourself, right? So let's generate things and allow the human to steer a direction and progressively, iteratively get to a place that either they would have gone, but it would have taken a lot more time, or sometime, and very often I have to say, to places they would not have gone without the system.
So is there sort of like a biggest common denominator that is usually necessary in art, and then the machine is sort of generating that or training on generating that, and then the human is there to do the refining touches, essentially?
Yeah, I mean, you know, the common denominator very often is what we call in computational creativity an inspiration set, which is typically your data, right? And there's been experiment and research which I cover in my cadency class. There's a course on aesthetic and the generation of new aesthetic judgments. So you can have machine multi-agent systems, for example, evolving their own aesthetics. But if you start doing this type of research without a human in the loop, it does work. And very quickly, some very novel aesthetic emerge. It turns out they are of no interest to humans. Right, and that makes a lot of sense because actually, yeah, and so this human in a loop, when it comes to that part of, you know, the cultural, subjective, aesthetic appreciation part of any sort of creative tasks, as far as I'm concerned, you know, is an open problem, and might stay so for a while, I have to say.
Yeah, definitely will. Thank you.
Great. Yeah, so on to Jean-Pierre Briot, if yeah. Oh, you're on mute.
Exactly. Yes. Thanks a lot. Well, I first a comment. I'm very impressed by your work, Philippe, and your works, I should say, because there are so many things and experiments. And so first, bravo. And I have several comments and questions, but I will just make one, or at least for now, regarding your MMM system, because of course it's I'm interested in deep learning as a basis of technique. Although I share with you the idea that it has some. It won't conquer everything, although it's progressing so fast with with mechanisms like attention, with adversarial, etc. But so my question is about MMM, because as you know, one of the issues using this kind of techniques is the structure, that is the lack of structure actually in the generation. So as far as I understand, your current system works for only a few bars, right? I mean, not very long sequences. And my point, it's more of a suggestion actually. It would be very interesting to see if this kind of in-painting is kind of completion mechanism could work if you could test it on a more higher level structural task, like which is very fundamental for a songwriter, that is from a part to imagine to create a B part, which is not just a copy of a part, but at the on the other hand, which has some link, some semantic link with a part. So I guess that would be interesting to do this kind of experiment. So just yeah, just a suggestion actually.
Yeah. Well, no, that's a really good question and a good point. It is true that our system is not limited to 4, 8. If you really have a lot of GPUs like we do on Compute Canada, 16 bars, and then we do moving windows. And often you wouldn't generate from scratch with that system. So you would actually have an already, you would import your own composition or a composition you want to start with. And that composition will have in itself already the structure. That's how we sort of solve the prime of the structure with that, but that's just a way around. Now, there is a need for hierarchical models that are aware that, pieces are made of phrases and sequence of phrases are forming parts, and sequence of parts are pieces, and a collection of pieces is a corpus of a particular composer and all that. Models are not aware of that for now, but we are working on it, and there's work going on to try to also modelize that at that level. And using deep learning, one of the main issues we have is we don't have the data set, as in we have the scores, but we don't have the annotations of what is a phrase in that score. What is a change of part in that score? For that, we don't have, at least not the big data. Yeah, and so that's an added complexity, because then we would have to an algorithm that does that for us first, and that's harder than the learning that comes after.
And maybe an additional question, if I can, or if there are not, or maybe no, I let it go for other speakers and questioners, and maybe I'll come back later.
Okay, great. Yeah, Cinda. Okay, so Cinda says. Okay, so Cinda asks, when will the MIDI corpus you mentioned be available, and from where?
Yeah, so that's submitted and under review at the ISMIA conference, the Symposium on Music Information Retrieval, and so I would say that it should be released before the end of the summer, if everything goes well.
Okay, great. Great.
Yeah, but if you are really interested in it, then you can also email me, because we do sit on it.
Fantastic. And then let's see, maybe last question from Lena. Happy if you're there, feel free to unmute, and if not, I'm happy to ask on your behalf. Okay, well, why don't I get started on her behalf? Well, what do you think about making use of the user's interaction with an AI system to train it in real time? For example, if one bar of music is regenerated by the user many times, then it might signal to the AI that it isn't doing a good job generating that bar, etc. So yeah, it's truly interactive.
Yeah, absolutely. Well, this is key, because in a lot of cases, you can't ask your user to enter too much data, and so one-shot learning is a big thing. There's many ways of doing it. There's algorithms for that as well, but often it comes down to getting, and that's what we do with Apollo, and getting the user to actually manage their own corpus and be like, okay, this is the songs that I want to overfeed the model to, for example. Or the other option is to have a latent space, like in a VAE, for example, and be like, okay, so this is, that song of the Beatles that I really like the style of, get me into this part of the latent space, and then I'll walk around and search around. So there's very, very, very many ways. Active learning, I see in the chat, is being mentioned as well. Exactly, there's a lot of option there. A little bit of reinforcement style learning as well. If you start being able, for example, to give feedback to musical agents like you would to a colleague in a band, or someone that is learning music. And so if there is really a lot of possibilities. I think we're just entering the moment where AI systems are good enough so that those questions of personalization, adaptability, active learning, all of that is just starting to get real, because we are just starting to have systems that are not going to be used only one or twice by our users, but are going to be used every day, multiple times. And for those systems, we have an opportunity to solve what is the most, maybe the most, the main problem that I find with computers is that the fact that, no matter how many times you do the same sequence of action in a given software, the software will never have the idea to tell you, like, actually, I just made a script and a new button for that set of actions here so that your life will get simpler. And so, yeah, right now, it is for the human to adapt to the software and not the other way around. And I think in the next 10 to 15 years, with the help of human-computer interaction researchers, we can change that status quo and make computers a lot more interesting to use.
Okay, great. Yeah, no, thanks. Hopefully that that answered your question, Lena. Yeah, great. So just in the interest of keeping everyone on time in their Zoom schedule, maybe we'll wrap things up now. But anyhow, I'd like to give Philippe a huge thanks. Thank you.
Thank you, everyone.
Fantastic.
Thanks a lot. Yeah, thanks, Michael, and bye now.